Hello and welcome back, everybody. We're on the worked example section for matrix inverses and determinants. I'm going to start off with a brief statement about infinite dimensions. In the past, we've looked at infinite dimensions and kind of decided that finite dimensions can behave similarly. But this is kind of the section where finite and infinite dimensions no longer behave the same, and our tools really only work very well in finite dimensions. So in infinite dimensions, I'll mention, and this deals with spaces, vector spaces of functions, right? That's what we want to think every time I mention infinite dimensions. There's a notion of determinant. But it is incredibly difficult to compute. So you'll recall in finite dimensions we have this theorem. That I finished the last video with. And the theorem stated that a matrix, and hence its associated linear map, has an inverse specifically when its determinant is non-zero. So this notion of checking if the determinant is zero is really useful for checking if you have an inverse, because it tells you if you should even go about trying to find an inverse. In infinite dimensions, this no longer really works because even though there's a notion of a determinant, since it's so difficult to compute, it's actually easier to compute the inverse than the determinant. So this idea of the determinant being non-zero to compute the inverse just doesn't really extend to infinite dimensions. Actually, it's even stronger than that. There are cases in infinite dimensions where the determinant is non-zero and it's still not invertible. So you get into some really murky territory in infinite dimensions. So we're not really going to worry about infinite dimensions with respect to this section in the book. And I think that's totally fine. I mean, in a lot of undergraduate courses, you never encounter infinite dimensional spaces. I'm kind of the instructor who believes you should be exposed otherwise. But, to each their own. So basically, we're going to be working only in finite dimensions for today, and a little while longer, in fact. With that said, let's get into some examples. So my first exercise that I'm going to bring up, we're going to solve the systems of equations 2x plus 3y minus z equals 4, x plus y plus z equals -1, x minus y minus z equals 0, and 2x plus 3y minus z equals 1, x plus y plus z equals 2, x minus y minus z equals 3, using matrix inversion. And the reason why I say that we should do this using matrix inversion is we'll just note right away that these coefficients in both systems are the same collection of coefficients. So in fact, the systems themselves are really the same, and the only thing that's changing is the right-hand side. So these are the only difference. That means really we could set this up as a matrix vector equation. So these are really the matrix vector equations 2, 3, -1. I'm just reading off the coefficients. 2, 3, -1, 1, 1, 1, 1, -1, -1, against the vector x, y, z is equal to the vector 4, -1, 0. And in the second case, the same matrix, 2, 3, -1, 1, 1, 1, 1, -1, -1, against the vector x, y, z is the vector 1, 2, 3. And I didn't quite make this super clear, but one reason why we can think about matrix inverses as solving this equation is you can think about multiplying both sides by M inverse so that M inverse M cancels on the left, and on the right we have M inverse against the vector that we care about. That's really why the inverse matrix helps us solve these equations. You can think about going M inverse here and here. It's an equation, so as long as you do something to one side, you can do it to the other side. In fact, you have to do it to the other side. And then when you have your matrix M inverse against the matrix on the right, there's always a notion of them canceling, and you're just left with xyz equals M inverse a vector, xyz equals M inverse a vector. So that's why this helps you solve for the variables x, y, and z. So in other words, we'll say something like M times a vector x equals a vector v implies the vector x equals M inverse v. So there's all sorts of different interpretations as to what the matrix inverse is doing here. But more or less, what is our job then? For today, it's to actually invert this matrix. So hence, we must calculate the inverse of 2, 3, negative 1, 1, 1, 1, 1, negative 1, negative 1. By solving the system, and I'm going to write it out as I did the last time, A, B, C, D, E, F, G, H, I. This will be our inverse. It's going to hit the matrix we wish to invert, 2, 3, 1, 1, 1, 1, 1, negative 1, negative 1. And we're hoping that this gives us the identity, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is always the identity ID. Okay, so to do that, we just have to perform the matrix multiplication on the left. So we're going to consider every term on the left as a row, and every term on the right as a column. And then as always, we perform all inner products of rows with columns to arrive at ABC on 2, 1, 1 is 2A plus B plus C. We have ABC on 3, 1, negative 1 is 3A plus B minus C. We have ABC on negative 1, 1, negative 1, which is negative A plus B minus C. We have DEF on 2, 1, 1, which is 2D plus E plus F. We have DEF on 3, 1, negative 1, which is 3D plus E minus F. We have DEF on negative 1, 1, negative 1, which is negative D plus E minus F. We have GHI on 2, 1, 1, which is 2G plus H plus I. GHI on 3, 1, negative 1 is 3G plus H minus I. And we have GHI on negative 1, 1, negative 1 is negative G plus H minus I. So that's the matrix multiplication on the left. We're hoping that this is equal to the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And now we just need to compare all terms. It's usually to my advantage to work row by row. Maybe I'll make this as a note here. So it's to my advantage to work row by row because this is what's really separating into three systems of 3 equations rather than one system of 9 equations. So let's just write this first row out. That's 2A plus B plus C. I'm comparing it to the 1 on the right-hand side. That equals 1. I have 3A plus B minus C. I'm comparing to the 0 on the right-hand side, so that's 0. Then I have minus A plus B minus C. I compare it to the 0 on the right-hand side. So this is really a system of 3 equations and 3 unknowns. Let's go ahead and solve it. What I can do is, the second equation is kind of asking me to solve for C. So I'll go ahead and do that and bring C to the right-hand side to get C is 3A plus B. I mean, you can really solve any of them in whatever order you want as long as you're following the substitution method, but that one looked like it would be a particularly easy one to solve, so that's why I chose it. I'm then going to plug that version of C into the other two, which is going to give me 2A plus B and then plus 3A plus B equals 1. And then in the bottom row, minus A plus B minus, and then in parentheses, so I make sure to distribute my minus sign later, 3A plus B equals 0. And if I simplify both of these, I end up with 5A plus 2B is 1. And if I simplify on the bottom and distribute the minus sign, I've got negative 4 copies of A, and the B's are going to cancel. So negative 4 copies of A is 0. That makes my life pretty easy because that's going to tell me immediately that A is 0. Now that I know A is 0, I can grab A plug it in up here, and in fact I can plug it in over here as well. Those are going to give me, since a is 0, 2b is 1, and it's going to give me that c is equal to b. And I just figured out that b should be 1/2, so c should also be 1/2. So there's b, c, and a, and then I can work on the second row of my big matrix. So the second row is going to be these three terms. I'll write those out as 2d plus e plus f. I'm going to compare that to the right-hand side. That has to be 0. I have 3d plus e minus f. I compare to the right-hand side as 1. And I have negative d plus e minus f compared to the right-hand side of 0. And as before, it looks like the bottom row is going to be the easiest. I can solve this for d pretty easily. I can solve for f pretty easily as well. Let's go ahead and solve for d. This is going to say d is equal to e minus f. If I go ahead and use that version of d in the earlier two cases, I can solve for those as we've got 2 copies of e minus f plus e plus f is 0. And then I've got 3 copies of e minus f plus e minus f is 1. And if I simplify those terms a little bit, that brings me to 3 total copies of e, and negative 1 total copies of f is 0. The latter one brings me to 4 total copies of e, and negative 4 copies of f is 1. The top line can be solved for f very easily. We find out that f is 3e, which means that I can plug in f as 3e here to get 4e minus 4 times 3e is 1, or in other words, 4 minus 12 is negative 8e is 1, and I recover that e is negative 1/8. Once that I've found e as negative 1/8, I can grab it, I can plug it in here for f. I find out that f is negative 3/8. And now that I know both e and f, I can grab f as well as e to recover that d is going to be negative 1/8 minus negative 3/8, also known as plus 3/8. I'm going to recover a positive 2/8, which is 1/4. So now I've found f, e, and d. And finally, if I want to encounter the last row here, that's going to give me a third set of 3 equations. 2g plus h plus I, comparing to 0. 3g plus h minus I, I'm comparing to 0. And negative g plus h minus I, I'm comparing to 1. We can simplify. Let's go with the middle case for I. That's going to give me that I is 3g plus h, and I can plug that version of I into the other two equations to give me 2g plus h plus 3g plus h is 0, and this can give me negative g plus h minus 3g plus h is 1. If I simplify the top row a little bit, I have a 5g plus 2h is 0, and the bottom line, I end up with negative 4g equals 1, because the h's cancel. And so this bottom row is pretty easy to solve for g, as g is negative 1/4. Now that I know g is negative 1/4, I can use it up here and recover that negative 5/4 plus 2h is 0, or rather 2h is 5/4, or h is 5/8. Now that I know g and h, I can grab h and g and plug them both in for I to give me that I is 3g, so negative 3/4, plus h plus 5/8. 3/4 is 6/8, by the way, so negative 6/8 plus 5/8 is negative 1/8 for I. So now I've found h, I to g, and that's everything I need for my inverse matrix. So my matrix, you'll recall, was ABC, DEF, GHI, and I'm just going to plug the numbers in. So A is 0, B is 1/2, C is 1/2, D is 1/4, E is negative 1/8, F is negative 3/8, G is negative 1/4, H is 5/8, and I is negative 1/8. You can see that there's really a 1/8 hiding in everything. If I wanted to pull 1/8 out, I could simplify the interior to integers. I get 0, 4, 4, 2, negative 1, negative 3, negative 1, 5, negative 2, 5, negative 1. So this will be M inverse. That's not quite what we were looking for, right? What we were looking for was the solution to these two equations. So what I actually need to do now that I've found M inverse is actually act it on 4, negative 1, 0, and on 1, 2, 3. So let's go ahead and do that. So M inverse on 4, negative 1, 0, and it's going to look like a 1/8, then 0, 4, 4, 2, negative 1, negative 3, negative 2, 5, negative 1, on 4, negative 1, 0. And this is always still considered as a matrix multiplication, even though the right-hand side's a vector. So we're going to consider all rows on the left-hand side along with the vector itself, and then perform all inner products. So the 1/8 can come along for the ride. We've got 3 copies of inner products. The first one's going to be 0 times 4 minus 4, well, we'll call it plus 4 times negative 1, and then we'll say plus 4 times 0. And then the second row against the vector will be 2 times 4 plus negative 1 times negative 1 plus negative 3 times 0. And finally, negative 2 times 4 plus 5 times negative 1 plus negative 1 times 0. If I go ahead and simplify all of that, I have 1/8 times 0 minus 4 plus 0. I have negative 4. Then I have 8 plus 1 plus 0 is 9. Then I have negative 8 minus 5 plus 0 is negative 13. And if I want, I can pass my 1/8 to the inside, and I recover the solution to the first system of equations. It's negative 1/2, 9/8, and negative 13/8. This would be the XYZ solution to the very first system of equations presented. If I want to find the solution to the second system of equations presented, this would be M inverse on the vector 1, 2, 3, and that's going to be 1/8 times 0, 4, 4, 2, negative 1, negative 3, negative 2, 5, negative 1, against the vector 1, 2, 3. So I have a 1/8, and then I'm going to be considering all inner products of rows against the column vector. It's going to give me 0 times 1 plus 4 times 2 plus 4 times 3. And then the middle row will be 2 times 1 minus 1 times 2 minus 3 times 3. Then the third row will give me negative 2 times 1 plus 5 times 2 minus 1 times 3. If I simplify everything on the inside, I've got 0 plus 8 plus 12, also known as 20. I've got 2 minus 9, negative 9. I have negative 2 plus 10 minus 3 is 5. If I pass the 1/8 to the inside, I can simplify 20/8. They're both divisible by 4. This is 5/2. And then I have negative 9/8 and 5/8. So that's going to be the solution to the second system in X, Y, and Z. So let's go ahead and talk about that 1/8 that was in front of my inverse matrix, right? This 1/8 kept showing up here. And I think every time you've seen an inverse matrix so far, there's been some number that we've been able to factor out. So let's ask the question, where did the 1/8 in front of M inverse come from? Let's go ahead and calculate the determinant of M, which in that case, the matrix M was 2, 3, negative 1, 1, 1, 1, and 1, negative 1, negative 1. Let's go ahead and calculate the determinant. Let's see if we remember how we do this for 3 by 3 matrices. We start by looking at the top row. We write out 2, 3, and negative 1, and then 2 gets associated to its submatrix. So we're going to look at the determinant of 1, 1, negative 1, negative 1. 3 gets associated to its submatrix, which kind of splits as this one. Determinant of 1, 1, 1, negative 1. And then the final 1 gets associated to its submatrix, which is determinant of 1, 1, 1, negative 1. And then we come through with a plus, minus, plus sign, and we compute. So at this stage, how do I compute? Well, I have 2 times the determinant of 1, 1, negative 1, negative 1. Recall we go AD, so this is 1 times negative 1, minus BC, which is negative 1 times 1, or CB, either one. And then we've got a minus 3 times the determinant of AD, 1 times negative 1, minus BC, 1 times 1. And then it looks like we have a minus 1 times the determinant of AD, which is 1 times negative 1, minus BC, 1 times 1. Simplify a little further, that's 2 times negative 1 minus negative 1, 0, minus 3 times negative 1 minus 1 is negative 2, minus 1 times negative 1 minus 1 is negative 2. Looks like we have 6 plus 2, 8. So that's the determinant of the matrix, and in fact the 1/8 in front of our inverse is because the determinant of M is equal to 1 divided by the determinant of M inverse. Or vice versa, the determinant of M inverse is 1 divided by the determinant of M. And so you have this really nice notion of determinants and their inverses, kind of how you'd expect with just numbers, that when you divide by it, you divide by it. That's where the 1/8 is coming from. You'll see that in really any sort of inverse matrix that you try to calculate, that there will be this term that kind of factors out. That'll end up being the determinant. You kind of get it for free when you calculate the inverse. So let's go ahead and run one more problem to make our lives a little bit easier. Do an exercise. Let's solve the system 2x minus 3y, x plus y. Let's say this is equal to 3, and this is equal to negative 1 for x and y. And you could totally do this by hand if you want to, but let's go ahead and write out our matrix 2, negative 3, 1, 1, and recall the two-dimensional inverse formula as 1 divided by the determinant. So we'll go 1 divided by AD minus BC. So minus negative 3 will be plus 3. And then we'll go ahead and swap the 2 and the 1 to give me a 1 and a 2, and put negative signs on the off diagonals to give me a 3 and a negative 1. Now, if you've forgotten where did that come from, let's just write it out over here again, because I can't stress this formula enough. You'll use it the whole semester. That's your inverse formula for a 2x2 matrix. And so that's the inverse formula here. Let's go ahead and grab my vector 3, negative 1 and place it right here and here. And we can arrive at a solution real quick. That's 1/5. And then we're looking at rows against columns. We have 3 times 1 minus 1 times 3, and we have 3 times negative 1 minus, or plus 1, negative 1 times 2 is going to give me minus 2. Looks like we have 1/5 on 0, negative 5, also known as 0, negative 1. Let's verify. If I put a 0 in for x and a negative 1 in for y, do we satisfy everything? We sure do. We have negative 3 times negative 1, which is definitely 3, and we have negative 1, which is definitely negative 1. So this immediately tells us x equals 0 and y equals negative 1 is our solution. So a bit of a quicker video today. I think everything is fairly straightforward, so I think that's why it kind of helps to make it a little quicker. Anyway, I'll see you in the next video. Bye.